The development of the model of the atom. Now the key thing to remember here is this note, that experimental evidence can lead to a scientific model being changed or replaced. So what we might have as our model at the moment may well be changed in the future, and it certainly has, the model of the atom certainly has changed over time. Originally, it was thought that the atom couldn't be split up anymore. They were just tiny spheres that couldn't be split up anymore. And actually the word atom comes from not being able to cut. And then the discovery of the electron led to this new model. And this model was what we call the plum pudding model. So let's go with our plum pudding model. And there was this idea that the atom is a ball of positive charge. So all this ball here has a positive charge. Sometimes it's drawn with a big plus in the background. So this all has a positive charge, a lot of doughy positiveness, and inside there are negative electrons embedded in it. A bit like plum in a pudding, or maybe you can think of it more as like chocolate chips in a cookie. The negative electrons are like the chocolate chips, and there's the positive dough. So ball of positive charge, you can think of it as the dough, and then inside we've got these negative electrons embedded. And this all seemed good, the model held well, until some new experimental evidence led to a change of this model. And that experimental evidence is what we can call the scattering experiment. So let's go with scattering experiment. And this was some research led by Rutherford. And what he did is he got some gold and he hammered it very, very thin. And gold is good, you can make it very, very thin. We've got some gold there. So you've got a thin strip of atoms. Okay. And he thought, what would happen if we fired some alpha particles at it? So he got a source of alpha particles, something that would decay and give off alpha particles. Let's put that there. And he encased it so that any alpha particles that were emitted all had to go in a set direction, and they all ended up being fired towards the gold leaf. Now this whole experiment was done inside a vacuum, so let's put inside a glass vacuum, and that way the only thing interfering, well, there shouldn't be any atoms in the air interfering because it's a vacuum, they've been taken out, so the only thing that should be affecting what's going on here is that gold leaf. And if the model of the atom is like a plum pudding, then these alpha particles, big sort of heavy alpha particles, should go straight through this doughy softness, this soft doughiness, should go straight through. And what he did is he put a detector behind it. So he placed a detector there, and this would actually flash each time an alpha particle hit it, and he found that lots of these alpha particles, as expected, went streaming through and hit the detector. Great. Theory seemed to be okay, but then he suggested, actually, let's move this detector around and see what happens if we place the detector here. So they placed the detector around a bit, and they found that occasionally, not very often, but occasionally, one of those alpha particles would hit the detector over here. Well, that was strange, because really they should be going straight through this soft doughiness. There shouldn't really be anything in there that's caused them to deflect. And in fact, there wasn't many. It was about 1 in 8,000, 1 in 10,000, something like that. And then he thought, well, let's try this detector in various places. And actually, he moved this detector around, so he tried it there. Then he tried moving it around further. And he even found that when he put it all the way back here as well, all the way back here, even then, occasionally, some of these alpha particles would be deflected or scattered so much that it hit the detector there. Very few really compared to what we're hitting it here, but there was some who had been able to deflect it, and he found this all the way around. Most were going straight through, huge majority were going straight through, but when he moved the detector to various places, he found that some of those atoms were hitting there. Now this was strange, because these alpha particles, as I said, should be going straight through, but there must be something that's deflecting them. And this helped a new model to be started to build up. And what was determined was, in that case, there must be something very large, not very necessarily large, but something very dense, with a very lots of mass concentrated right at the centre here. And let's just jot these down, these conclusions. So, the mass of the atom is concentrated at the centre. Well, why is that? Why did you know that? Well, most of these alpha particles were going straight through, but sometimes they were getting close enough to the centre of an atom to be deflected. Okay? It must have had enough mass to be able to deflect it, so enough charge, and in fact, as the alpha particles have got a positive charge, the centre of the atom must have a positive charge. So he started to call this the nucleus, this mass in the centre. If the positive alpha particles are being deflected, that would suggest the nucleus in the centre has a positive charge. And the other thing he noted is that this nucleus that he's now calling it was actually very small. So this idea that sort of only about 1 in 8,000, 1 in 10,000 or so. About 1 in 8,000 or 1 in 10,000 alpha particles were deflected. The rest didn't come near enough to the nucleus in the centre. The fact they were deflected suggests it's got a positive charge, and the fact that they were deflected at all suggests there must have been enough mass and enough positive charge to cause these fast-moving alpha particles to be deflected in the first place. So we've now got this idea that instead of having this doughy ball of positive charge, there must be something in the centre. And this is what we now call like the nuclear model. So it led to this nuclear model, where we have a nucleus in the centre, this idea of a nucleus in the centre, and electrons zipping around the outside. And actually sometimes they show them taking these kind of paths like this. These negative electrons going around the outside. Later, some more work was done by a chap called Niels Bohr, and he suggested actually rather than having these electrons orbit sort of randomly, they had these fixed positions. So this model here was then developed a little bit further by some research by a Danish man called Niels Bohr, and he altered this model further to have still the nucleus in the centre, but these electrons orbiting on set orbits, shells, energy levels, various terms in different subjects. So let's put the little symbol E for those. So Niels Bohr developed it further, but this was a nuclear model with a nucleus, and it was developed further by Niels Bohr to show them at set positions. So we started with this plum pudding model, then we had some new experimental evidence from our scattering experiment that showed, hang on, there must be a mass of something right at the centre with a positive charge, and it's got to be very small. So this idea of the nucleus came about. So we had to adapt our model from the plum pudding So this model, the nuclear model, and then this was further developed by some research, more new experimental evidence from Niels Bohr, suggests that actually it's not so random where the electrons are, there must be fixed shells or energy levels where they're orbiting.